how do I do that?
Click on the chat.
It's too late. We're live, Morgan. The whole world sees it.
Let's see if I can remove it. There you go.
All right.
Thank
So
you, Ken.
it's July 10th, 2014, 11 a.m. Pacific. This is DB Hangups, and today we're going to be talking about indexing. For those of you who are not on the Hangout, you missed some silly times with some of the Google Hangout apps that we were messing with, and I'm sure they might make an appearance during this Hangops. But yeah, so today we're going to be talking about indexing. I'm Jeff Anderson. I'm a DBA at Box. And a quick round of introductions. Why don't we start with you, Jerry?
I'm Jerry Narvaja, sales engineer at SkySQL and co-host of the RSQL podcast.
Okay, and Morgan?
Morgan Tucker, MySQL Community Manager at Oracle.
And Tim?
And I'm Tim Callahan from Tokutech, and thanks to today's topic, I finally have something to talk about on this show.
Well, in that case, Tim, feel free to get us started. It's actually a completely open book today, just anything about indexes. I have a few bullets that I want to make sure we hit, but I mean, we can go anywhere with this today.
Okay. I wonder how we should kind of dig in and get started. So,
what about the sign on your back?
Low queries need to be optimized or removed. Yeah, that's always an interesting one. I wanted a couple more minutes to prepare, if possible. If you guys can talk for a minute, I have a slide or two I can probably share that would be helpful for me to talk about my side of indexing.
Sure.
Yeah, that would be great. So, I mean, the first, just the couple of bullets that I have, and the first one I want to hit on is just in general, indexes in MySQL. And I mean, I guess you could just say indexes and databases in general. For folks, for a very basic level, if you haven't had to deal with them before, and understanding what the benefit of them is. With MySQL, everything typically, at least with InnoDB, is a clustered index. So everything is going to be keyed off of your primary key. And that is going to be the typical way you're going to do your access patterns. So when you're defining your table, in your nice normalized format, you're always going to have a primary key marked on one of those fields that is meant to be genuinely unique for the whole table and is effectively your lookup into that table. So in MySQL, you have your primary keys that you put on the tables. You can do unique keys on other fields to guarantee uniqueness in the table for some other business constraints. There are full text key indexes, which allow you to do text searches over an index in a certain way. And a couple others, hash indexes. There's some geospatial indexes that I've never used. And I think that's it in MySQL. Feel free to chime in and correct me, though.
You're right. What I'd like to... I'm not on the screen. That's odd. What I'd like to add is the following. There are some MySQLisms, and one of them is InnoDB. If it doesn't find a primary key, it creates one of its own. And the criteria it uses is if it finds a unique key, then it uses that unique key. And if it doesn't find the unique key, it creates one of its own based on row number. However, the disadvantage of these is that you don't have access to these keys and you can't control them. And they're hidden, and sometimes that's a bad thing because you cannot do joins on those keys. They cannot be used to optimize queries or anything like that. So it's usually recommended that you define a primary key on the InnoDB tables. That way you can, if you need to join on that key, you can. Otherwise, it creates overhead. The second thing is, and I'm sure Tim might say something about his, because I know his presentations, is when you define secondary unique keys, as you said, it guarantees uniqueness, but on the other hand, it means that every time you add a new record, InnoDB has to do a search by that key to guarantee its uniqueness. So you're adding a lot of I/O operations, both in writing and reading. So that's my 2 cents on keys and MySQL.
Sure.
Cool. So I actually had a quick comment or question for you, Jerry. So you had mentioned, if you don't define one, it'll walk through and try to identify one. like picking a unique key first if there's one in the table. So if you define a primary key on a varchar field, for instance, does MySQL still use that as the primary key, or does it still create that kind of implicit auto-increment row number?
I believe it uses the varchar as primary key, which is one of the reasons why you may want to avoid, if possible, varchars on the primary key. It creates challenges of its own.
Cool, and that's actually something I think we'll loop back on later, just the challenge of having text for your indexes.
Yeah.
And that's actually,
it's so tough.
As part of this conversation today, I want to throw some stuff out there, and you guys are certainly welcome to bat me down. I wish Shlomi and a few others were on. Maybe they'll join in a little bit. But what you just brought up reminds me of something that I see from time to time where I think as database administrators, when we're building applications, it's not often that we find a primary key in the wild. Like in our data, oftentimes our data doesn't really have something we would consider a primary key. So
right.
in TokuDB or InnoDB, you go with an auto-incrementing primary key, or you don't define it at all and you get one behind your back. But I find many times people have performance issues, and a lot of times the issue is they've declared a primary key only because it is the primary key, not because it needs to be the primary key. So they're not declaring a primary key to make sure they don't have duplicate data, they insert the same row twice. It's just, hey, I created a table, and I noticed that these 5 fields in combination are unique, and I'm going to declare that as a primary key. And that has really bad side effects with your secondary indexes in InnoDB, and that the extra payload that's being stored is much larger than it has to be. So I don't know if I'm not thinking through the whole problem, but I find oftentimes with people, the first thing I see when I see a natural primary key, especially if it's wide, is why is that? Are you declaring that because you need it to be the uniqueness check, or is it just you noticed it was unique in general?
Right. I've had this realization and problem as well. And I've noticed cases where it's good and bad, which is really hard to make generic advice. Mm-hmm. I noticed you use the word natural primary key for when it naturally occurs in data. And I think it would commonly be referred to as a surrogate key if it was something that had to be added, like an auto-increment key. Mm-hmm. And I know particularly if you have a lot of secondary indexes, then sometimes using a wide natural key is a very bad idea. But if you have a natural key and you don't need many secondary key indexes, it can be a good idea as well.
Mm-hmm. All right. Jeff, can I share my screen for a little bit and cover a few of my generic slides that speak to indexing in general?
Yeah, go for it. Let me grab the cameraman app. But go ahead and get set up for that.
Do I need to just turn on screen share to do that? I haven't done it in Hangouts before.
Yeah, just hit the screen share button, and then it'll pop up a list of windows you can choose from and pick the one that you want to share.
Cool.
Alrighty, we see a PowerPoint, it looks like.
Yeah, as soon as I tell my Mac that it's okay for what was just about to happen. All right. Can you see it?
Yep.
Okay. So, I think this is good foundation for indexing conversation in general. So, the majority of indexes in modern databases, call it Oracle, MySQL, SQL Server, InnoDB, to a limited extent TokuDB, which we'll talk about in a minute. Everything is based on what's called a B tree. Technology that was developed in the early 70s, and the foundations of it is it's got a really interesting property in that it keeps data in sorted order, and it gives you some nice properties with respect to how many operations you have to do to find data. And finding data might mean just looking for a single row. It might mean looking for a range of rows. But a traditional B tree is going to look like this underneath the covers. You're going to have these rectangles are called nodes. And in the top levels of the tree, these, I like to refer to them as internal nodes. So these internal nodes are really there for guidance and helping you find things. And the way they do that is they have, this is a very simple B tree with a fan out of 2. So you have a pivot in the middle and pointers going down. So at this very top level of the tree, you throw in a value. So if I had 10 rows of data in my database and 5 were left and 5 were right, the pivot at the top might be the number 5. And if I'm looking for something that's, the key is the number 6, then I would follow the rightmost path. I would say, it's greater than 5, so I go right. When things are less than, you go to the left. So these pivots help you understand the path to the data. You're following pointers, and then down in the bottom, instead of calling the bottom nodes in this tree an internal node, they're called a leaf node. And in most databases, what goes in the leaf nodes is the data itself. So the higher level nodes are all about a path to the data and keeping things ordered, and then the bottom is actually storing data. So in something like InnoDB and MySQL, what you're going to have down here is the actual rows themselves in the leaf nodes. The limitation you run into, looking at that picture, these were developed back in the early 70s when, pretty much what they were building, everything fit in memory. So this is an awesome data structure for in-memory data. And in-memory doesn't necessarily, what shouldn't come to mind is MemSQL or VoltDB or times 10 by Oracle. By in-memory, what we're really talking about is the working set of your data. Your data can be much larger than main memory, but if the last week's worth of data fits in main memory and everything going a year back is at disk, for the most part, if you're only operating on fresh data, it's going to perform like an in-memory system and be very fast. And that's something InnoDB has amazing in-memory workload performance. It's something we strive to at TokuDB. I don't think we'll ever get there. There are many more engineers still focusing on that problem, and when you watch Dimitri's benchmarking talks, he just takes his numbers higher and higher and higher, especially with respect to this in-memory performance. Where things go bad and get slow is when everything doesn't fit in memory. So most workloads nowadays, you're not going to have deep enough pockets to buy an unlimited amount of RAM and put them in your server. If you're on EC2, RAM is a big cost factor in terms of the bigger RAM in your instance, it gets expensive in a hurry. So in the prior picture, we could pretend everything fit in main memory, but in the real world, systems look like this. So you're probably going to be able to fit the upper nodes in your tree, the internal nodes in memory, so you can easily find the path to data. But chances are, when you have enough rows in your tables and enough tables in your system and enough of a workload going on, that you're going to fit a handful of these leaf nodes, or definitely not all of them, in memory, and the rest of them are going to be on disk. So anytime you wanted to do a query, for example, just a simple select statement on the primary key, you're going to follow this B tree down, and if you're looking for the key at 100, it's to the right of 22, to the right of 99, and InnoDB, for example, or even TokuDB for that matter, it's going to say, okay, I need the leaf node that's to the right down this pointer. It's going to notice it's not in memory, and it's going to actually ask the disk for that block. So while that block is coming into main memory, that query is stalled and waiting for the data to arrive. Spinning disks, you're measured in milliseconds, 4 to 5 millis to peel something off of disk. SSDs make that a lot nicer. That you can measure I/O oftentimes in microseconds, not milliseconds, on decent flash or PCI stuff. But here's the challenge with modern day databases: is RAM is never going to contain data. Data continues to outpace. The amount of data we collect tends to outpace the amount of RAM we can afford. So this is a kind of an ongoing problem. This is a slide specifically about fractal tree indexes, but I definitely want to tip my hat to InnoDB in respect to this slide. So if we look back at this prior slide, so your primary key in InnoDB is a B tree, and every single secondary index you're maintaining is also a B tree. We did an insert example where I said, okay, or a select example where I wanted PK100, and I followed down here, and it wasn't in memory, so I had to go to disk to bring that leaf node in to actually understand what the value of the row was with PK100. If you take the operation of an insert, the same thing happens. So when you insert data into InnoDB or TokuDB or others, the same thing's going to happen. So if you wanted to insert the row where PK was 100, primary keys have to be unique. You have to take a look. So you follow down this tree, you notice, hey, the leaf node where row 100 would be stored isn't in memory, so I'm going to go peel that off of disk and do the work. What InnoDB did years ago, 2008 or 9, if memory serves me correctly. So every primary key is a B tree. Every secondary index is also a B tree. InnoDB added something initially called an insert buffer for secondary indexes, and that's been expanded over a few releases now to be both inserts, updates, and deletes, only on secondary indexes. And then the goal of that buffer is to avoid this I/O problem. So when I'm inserting data into the primary key, I have to take the dip, peel something off disk, and do the work. I'm maintaining secondary indexes on that same data, and this change buffer, they call it, allows me to buffer that change and not have to do it immediately. And what I do is I have this one big, very large buffer here. TokuDB and Fractal trees have many buffers, but InnoDB on every secondary indexes, it maintains this change buffer. I highly recommend people read up on it. It's on by default. If you want to see how important it is to your workload, I challenge you, turn it off for a little while and watch your insert, update, and delete performance tank if you have secondary indexes. So the goal of that buffer is to avoid having to do an I/O every time you're inserting something or deleting something or updating something in a secondary index. And it's a buffer. It's the documentation's a little fuzzy on exactly how large that buffer is allowed to become. But as I said, if you turn it off, you'll see a huge difference in the performance of your system. And there are limits, like it won't allow the entire InnoDB cache to become nothing but those change buffers, because then you'd be forcing out leaf nodes you need to be seeing, as well as internal buffers to get going. So the intent on this slide right here, when I'm normally doing a presentation, is just to compare and contrast. Fractal tree indexes are what TokuDB is built on. Traditional B trees are what InnoDB uses. So InnoDB's got that change buffer, which is a nice addition for secondary indexes. But what Fractal trees do is they add this buffer. We call it a message buffer, and we attach a message buffer to every single internal node in the system. So we're doing something similar to InnoDB in that we're buffering inserts, updates, and deletes, which is allowing us to avoid I/O. Really important. A fractal tree index is a lot like a B tree, as you can see at the bottom. You know, two huge similarities. We're going to the actual row data, when it's finalized and doesn't have messages above it, it's going to go down in the leaf nodes. And we're using this B tree. It's an ordered tree, so it's good for things like range scans. We've got these message buffers all over the place, which is a big difference to a B tree. The other big difference versus Inno directly is buffers, is these node sizes. So in InnoDB, the biggest one of these internal or leaf nodes can be is 16 kilobytes. And it can be smaller. I believe you can do 8K and 4K nodes. It's not allowed to be larger. And I see in the Maria documentation, I think for Maria 10.1, and Jerry, you can correct me if I'm wrong, I believe Maria is adding support for 32K and 64K node sizes. The main reason bigger nodes are interesting and important, in my mind, is compression. Compression's a big thing there. So in InnoDB, when you turn on compression, the largest unit you're compressing is 16 kilobytes. And if you've played around with things like WinZip or PKZip or gzip and such, you'll know that bigger things tend to compress better because the compressor has an opportunity to see more about what's going on before it makes decisions about how to compress data and looking for redundant data. So big things compress better than small things. So by having these nodes themselves be 4 megabytes to start, it gives TokuDB an interesting advantage when it comes to compression. The other thing to keep in mind is that although this entire node itself is 4 megabytes, we chop it up into something we call a basement node internally. So we're actually not compressing at the 4 meg size. It's user definable, and the default is 64K. The reason that's important is if when you went to do just a single row lookup, reading 4 megabytes of compressed data off disk, uncompressing 4 megabytes just to return the user 50 kilobytes, let's say 5K for a single row of data would be extremely inefficient. So we break that up and make it a lot smaller in the fractal tree itself. But that's the large, the interesting thing that for fractal trees is really these buffers. There's lots of them, and the other interesting thing is they can hold anything that we can. They're called message buffers for a reason. They're not single purposed to understand like insert, update, and delete, for example. So these buffers, and here's an example. Anything could be a message. So these message buffers are how we created agility without downtime. So in that message buffer example, if I have a table and I want to add a column, behind the scenes, all we're doing is introducing an add column message to the very top of the tree that slowly works its way down. So instead of something like InnoDB where the table gets rewritten, or in modern InnoDB, it does it in an online way, but it's still rewriting the table behind the scenes. In TokuDB with these fractal trees, we can add columns on the fly instantly, and this message gets applied from that point forward. So if the user, after adding the column, immediately selects a row, we materialize that column, kind of in a virtual way, right, just before we provide the row back to the user.
So I have a question on that stuff, Tim. How
Sure.
Is the size of these message queues, are they definable by the user, or is it something that's kind of built into the software?
They're user definable, yeah. So on this slide where it says these nodes are much larger, so in a B tree, and a fractal tree is a lot like a B tree, you really want nodes to be the same size. And a huge reason for that is you're managing a cache, and when you're putting things on disk, you want things to fit in the same places. So by default, all these nodes, the internal nodes, which have message buffers, and the nodes at the bottom, they're all 4 megabytes by default. It's a user-definable parameter. So when you create a table, that's your opportunity to say, okay, I want this table to have 1 meg nodes or 4 meg nodes. That's a knob we don't tend to turn that much. And the origin of that knob was when a fractal tree was created. There's a lot of math and algorithms and data structures behind the theory. The initial theory was we wanted to do as much bandwidth of pulling data off the disk in the amount of time it took to get to that spot on disk in the first place. So I think the math was if it takes 6 milliseconds to get to, on an average read for latency, we wanted to do 6 milliseconds worth of throughput off of that disk because we induced the I/O in the first place. So these are knobs that, in a world of Flash now, I'm starting to play with as a benchmarker and working with users to understand, does 4 meg make sense for SSDs? Does a certain basement node size make sense for SSDs versus spinning disks? But they're all parameters that can be changed.
It kind of reminds me with larger pages, what can happen is sort of like a memory dilution. If you have a very OLTP, point lookup workload, only a couple of rows in each page are very hot. But if they're spread across many pages, then the whole page gets caught in memory, so it inflates the memory requirements a bit.
Yeah, and that's what we learned. As I mentioned, these leaf nodes, and I'm happy you guys heard all that because there was dead silence while I was talking. I was nervous. I was talking into a dead mic.
But I just didn't want to interrupt you.
No, that's fine. So the original implementation of a fractal tree index, the leaf nodes at the bottom, like I said, they were 4 megabytes. And what that gave us was amazing compression. So when you're compressing something that's 4 megabytes, you get better compression than you would if you broke it up into smaller chunks. But the problem was for a point query, if I have a table with average row size of 50 bytes, if that leaf node wasn't in memory, I had to peel 4 megabytes of compressed data off disk. I had to decompress it, and that takes a lot of CPU. Deserialize the entire thing just to give the user back, let's say, not even 1% of the data I just bothered getting into my cache. So to your point, Morgan, I've now evicted a bunch of stuff from my cache that was probably useful. So that was TokuDB version 1.2.3, circa 2010-ish. So I think in version 4, we added a concept called a basement node. So we're now taking this leaf node, chopping it up into something that currently is by a default of 64K. So if something in the leaf node gets hot, I only need to consume 64K of my cache because I can just bring in a chunk of the leaf node. I don't have to bring the entire leaf node into memory. Comes off disk faster, decompresses faster, deserializes faster, evicts less to get it into main memory. So that was, we were creating an interesting new kind of technology, and we've learned along the way, some original design decisions were not the best decision in the world, and how do you evolve around that? The other thing that brings to light is, one way you could look at this as the word fractal. People often ask, why is it called fractal? Well, in a way, this leaf node right here is kind of a little mini fractal tree in itself, because it has a little header at the top that's got pivots and pointers to all these basement nodes that are contained in. So if you zoomed into a leaf node, it actually kind of looks like the fractal tree that it came from.
Cool.
So that is it for that piece right there. And it's interesting to me too. I'm always, I'm kind of a benchmarking fan, and always thinking about some of these trade-offs, right? The trade-off of one of the trade-offs of compression is you got to decompress the data. It makes it a little more latent when it comes into main memory, and therefore, users sometimes come to us and they say, "Hey, I love your compression, but in isolation, I run this one query and Inno does it in 0.29 seconds, and TokuDB takes 1.3 seconds. You're 5 times slower." And sometimes the only right answer to that is I nod my head and I say yes. Like, do you want 10x compression? Well, you're going to pay something for decompression.
Right.
So you can't be everything to everyone, I guess, is the point.
I love those examples.
Oh, they're fun, yeah.
The examples I like even more is the really short queries where you spend more on network latency. I mean, they can matter with replications if they're modifications. But.
Yeah, or the one where they say, "Hey, I run MySQL slap and I put 1,000,000 rows into my ISAM one row at a time, and it's faster than InnoDB, and InnoDB is faster than TokuDB." And I say, if that's your use case, then I think you finished your evaluation. I've yet to meet a MySQL slap application, but maybe there is one on the planet somewhere.
Well, I met tons of those, and they're not necessarily the way to go. And every time you say, "Have you tried a batch insert?" they said, "Oh, really?" And then they find out that InnoDB or TokuDB are as fast as my ISAM. Anyway, the question I have for you, Tim, is: have you looked into atomic writes when writing to SSDs or Fusion IO cards? The thing that the work that MariaDB has done for Fusion IO with InnoDB, because it writes in much smaller chunks than the typical page, and it achieves some optimizations on Fusion IO cards. I don't have all the details and all the technical details, and some of them are really dry and difficult math. But
we have that in 5.7.2. I can explain a bit how it works if that's something that helps. So InnoDB has something called the double write buffer to prevent torn pages, where you're trying to do a 16K write and you have a crash halfway in between. So it writes to the double write buffer, which is a little space in the main table space file by default. It can be separated out, and then once it's been written there, you write to each individual destined page. But if your underlying storage device can guarantee that a write will always be atomic, you don't need to write to the double write buffer. And so the Fusion IO enhancements detect on startup that the underlying device can do atomic writes, and then they just ignore the double write buffer.
Yeah, I know I've heard the explanation before from Toku Tech Engineering. We don't need a double write buffer. We can't suffer a torn page. But
okay.
Back to your original comment, Jerry. It's nothing we've planned yet. I think there's interesting stuff coming with that. Also with respect to, I've seen some stuff, and at Percona Live they talked about compression, and one way to deal with compression is to just let your storage do it. And I think there's some interesting aspects of MySQL or Maria using a flash device with that kind of driver and getting the compression out of the flash device itself, and just being, throwing your hands up and saying, "Hey, it's not my problem. Like, it'll go to disk and come back the way I want it, but they're going to deal with compression over there." Which again, if Inno could start pushing bigger things at it, bigger block sizes, I think you'd end up with slightly better compression on that. Jerry, I'm looking at the Maria page right now because I know I read it recently. Do you understand the driving factor behind Maria 10.1 trying to get the InnoDB page size to be 32 and 64K supported?
No.
Because what's interesting to me is, I would think
can research it for the next.
Okay. I would think the most interesting thing about bigger blocks would be compression, but right on the page it says compressed tables can still only be 16K or less, so it's kind of, or I get maybe range scans on secondary indexes would be assisted by that. But Morgan, I assume there's, to your knowledge, there's nothing going on at Oracle in that direction?
Nothing we've talked about publicly. I know we've done a lot of research into that. We care a lot about new storage devices, fast SSDs, and things like that, and working better in environments with network-attached storage as well.
Yeah,
It's probably not so useful for SSDs, so maybe that's a bad example of the site, but it is a large part of the work that's happening.
I'd imagine adding support for bigger blocks is much more than just a pound define in a header file. It's probably there are probably many reasons that it's not easily changeable or desirable.
Yeah, but I mean, ultimately, doing something like that might allow just for better disk access when fetching certain types of data. And I mean, the biggest ones coming to mind are text or large varchars, right?
Right.
And maybe just the idea of like in Oracle. I mean, I think actually just love in Oracle. There's the varchar data type, and then there's the varchar2 data type. And one of them is SQL compliant, and the other one is Oracle's kind of take on what a varchar should be. And this is not Oracle MySQL. This is like Oracle RDBMS.
Right. But I think you nailed it, Jeff. Large pages will be actually very useful for blob data types.
Yeah, and that's
less efficient with blobs or text blobs. Group it all together. It's the same for InnoDB. We're less efficient there than we could be.
And I mean, just actually to drive this back towards indexing, a classic example, and I was just messing around in a sandbox a couple minutes ago. When you try to create an index on a text blob field, so a field that is a varchar or just text, you have to define a prefix of that blob effectively that can be used, that can be indexed. You can't index the whole thing. And that's in part, at least with InnoDB, that's in part because large text objects are punted off page onto a separate page, typically, just because it's too costly to store them on the same page. I mean, 16 kilobytes, you can't fit that much. And when you start factoring in, like, I have a varchar 255 field that I'm trying to index, and I'm using UTF-8, which means this field has the potential to be 3 bytes for every character. That's 768 bytes just for a single record that you might have to do. 4, sorry, wow.
UTF-8 MB4, it'll be 4. Yeah.
That actually brings an interesting question. In MariaDB 10, you have actually MariaDB 5.5, you already had dynamic columns, which is a blob that is structured as similar to a document in MongoDB, and it has functions to extract the fields on that blob, and you can define virtual columns, and those can be indexed even. However, that's a lot of overhead to structure a blob. But I'm wondering how it would work in those cases with bigger data pages or cache pages. I'm sure it's going to be much more efficient.
Yeah, I'm just wondering about those in general because, I mean, whenever I get a schema to review for a new field or a table being added, one of my favorites is when we come across something like it's a large varchar field and they're going to put a comma-separated list of IDs in it or something, which there are better ways to do that, right? And everyone smiles when you say that.
With a leftmost wildcard to find what they need.
I love when they try to justify why they do that.
And that's the thing is, there are times where that type of denormalization is okay, but the biggest concern I always have is, unless we have strict mode running on the server, that data can be truncated potentially if you blow out the size of the maximum with the field. And so just trying to account for those things and putting more structure around those types of pieces of data. I mean, there's so many examples, and that actually just goes into a whole realm of like basically data types for what you're trying to store. I mean, how many times do you see IP addresses that are a varchar, what is it, 15 or something? Yeah, where people put the dotted notation IP address in, and it's like it's actually a var binary might be better for that.
Not to mention that you have the functions to convert them into an int, right?
Exactly. Did you have something?
Yeah, while we're talking about indexing, like let's say someone creates a schema with a varchar 1024 2048. I think the max index key size in InnoDB is like 700 and something or 1200 something. Just let's pretend it's a number smaller than this varchar. Is there a real-world use case on this planet where it makes sense to index the full 2K varchar?
I could probably try and take a stab at answering that.
Okay.
So far, we've talked about indexing, but we haven't talked about constraints.
Mm-hmm.
And so when we talk about secondary indexes, they could be a non-unique index, or they could be a unique index.
Mm-hmm.
And you can't apply constraints without having indexes, at least in any database that I've ever worked with, because it'd just be impractically inefficient. You could index on the prefix, no problem at all, in that varchar 1024 or 2048.
Mm-hmm.
And every data type I've ever looked at, you can get great cardinality off the first 20 or 40 bytes, no problem at all. But you couldn't apply a unique constraint unless you had the full string. So I think in terms of constraints, sure, the argument exists, but otherwise, as you described, you were talking about just indexing. It's not quite a use case.
Yeah, because I mean, it's like, if I have a customer database, I want to run a report, show me all the customers from Massachusetts, right, MA.
Right.
I'm trying to think of a varchar 2048 example where, like, an exact match is any more important. It's one of those things where, like, you build. I mean, you were talking about how InnoDB stores data, and the pages are this size, so big data gets, big rows get stored, partially elsewhere. That's another huge difference between, our larger node size allows us to do that differently. So in TokuDB, everything is in line. We don't put blobs and texts and things elsewhere. It's right there in the row. So we have a defined maximum row size that I think is probably substantially lower than Inno. But if someone wants to store 4 gigabytes in a row, I say that's a great InnoDB use case, Morgan, and I'll send them your way.
Thanks. And I'll actually be pretty sad because there's other problems.
And you'll try to send them back.
There is a use.
I just want to pause there. Do not store 4 gigabytes of data in a row.
Well, I had that discussion for 20 years, and I haven't convinced anyone yet. People convince themselves after they try. But literally for 20 years discussing that particular use case. Anyway, going back to the 2048 or 2K varchar and having a unique index, the use case I come across for that is there's software that catalog the full URL of a position of a file on disk, and especially when they go through network disks and the URLs or the full path can be pretty long. Some people try to create that URL, make it the unique key.
Mm-hmm.
And if you add path names, file names, and all that, you can get pretty big pretty fast. Okay. And there's one particular music player in Linux called Amarok that you cannot move the tables from MyISAM to InnoDB because it indexes on URLs and it goes beyond the maximum allowed size for varchars and a key for InnoDB. Although with InnoDB 5.6, I think that restriction has been extended, to much bigger indexes, I believe, Morgan.
I can't remember off the top of my head, but it was changeable earlier if you were willing to change the file format. InnoDB something format.
Yeah, but this is an Amarok. This is a player that comes, for every single distribution under the sun. So right. KDE, of course.
Yeah, I was going to say, if you're running KDE primarily.
Yeah, exactly. So I don't think that changing the setting there is an option because it's so, it has to be so generic that it doesn't apply. But I believe that
that's the same if you're WordPress or Drupal. You can't assume that you could ask your customers to change a MySQL setting that's a server specific. Requires a restart. I do agree that it does become a limitation.
Yeah, actually, so an interesting question I had on that then is how does just a regular key that you would define in InnoDB differ from doing a full text index, for instance, in 5.6 with InnoDB? Like, does that actually allow you to index more? So the disclaimer here is I've personally never had to use a full text index. I've actually converted full text index to regular ones because they weren't being used as full text keys.
Yeah, they're quite different how they work internally. So when you set a regular index on a column, it's that B-tree index that Tim described. When you set a full text index, it chops up or tokenizes each of the words in that data type, and then it stores it in internal tables internally to be able to search. I think the structure, it's close to a B-tree. I don't know if there's any changes to that. But the other differentiating feature with a full text index is that it has to provide ranking as well as providing results. So there's that match and rank that makes it quite different.
And it has to provide proximity and a bunch of other functionality that full text indexes have that regular indexes do not have.
So, I mean, but given that, though, does that mean, if you potentially maybe you're hitting the upper boundary on setting just a regular index on a field, could you just use a full text index to satisfy that, or does that not work?
Well, could you versus should you kind of in this, it provides different functionality, but I think in many of the use cases where you do have a very long varchar and you want an indexing, you probably did want full text indexing. Let's be truthful with that. The only constraint that I can think of immediately is the one that Jerry brought up, where maybe you wanted to enforce a unique constraint, and you can't do that with a full text index. The closest you could do is probably have a secondary column being an MD5 of that value and add an index on the MD5, and then hope you don't get collisions. And you've got close to uniqueness.
And Jeff, I think you're touching on an area where our roots in relational and schema, in a way, if you look at something like MongoDB, you gave an example of the user, someone came to you with a schema and they have a varchar 1000 and they're putting a comma-separated list of integers in there. Jerry talked a little bit about Maria, and I think they've got some work in this direction already. But if you take a product like Mongo has call it a data type of array, and you can index an array field, and almost like a full text, it basically creates a secondary index and drops every value in that array into that secondary index, and it has a search language that's very natural for saying, hey, give me any document that contains this in its array. I think Maria has code in that direction. They might even have something very similar, minus the indexing piece, but I think being able to express that use case and query on it. But I'm hoping we're working in that direction, because as old school relational guys, what we think is, well, if you really wanted that functionality, you should have created a second table and used the same primary key as this table, and before you know it, it's just confusing for us as DBAs. It's confusing for the guy writing the app, when it should, hopefully we can evolve to a point where that just is supported. And then how we get that expressible in SQL is a whole nother a whole nother ballgame. But that's what we want for the use case you just described. Is we want a field that's an array of values, and for those values to be indexed such that lookups can be supported very efficiently. And everything else is how the sausage gets made. We want someone else to just make it happen.
Yeah, I totally agree. It's a valid use case. It's something that the relational model doesn't quite map to. I hope the SQL standards committees jump in here as well and help out. They kind of did, or thought they did, when they added XML features.
I was about to say XML kind of started to address some of that, but there's a lot of text in XML.
As soon as those features were introduced in every major database, nobody used them, from what I can see. So
JSON's the next big one that's being done right now, right? So. But yeah, I mean that's a really good point though, Tim. Just at what point do you stop trying to slot in these other type of data structures into the relational model, and when does it make sense to do it elsewhere? And I mean, there's been plenty of times just when it comes to that, when we're looking at things, does it make sense to store MySQL, or do we start going down the route that large other companies have done, like LinkedIn and Facebook, where we're just using MySQL because it has this really efficient storage engine, and we're putting a small layer on top that treats it, that exposes it to be effectively a graph database or something. Versus using something like Mongo, which does just do document store out of the box, or maybe Solar Cloud or Elasticsearch or something on top of Hadoop or HBase. And so ultimately that comes back to the thing of what is available in your environment, what are you able to support, and how is its performance and the manageability of it compared to maybe trying to go through the effort of slotting it into a relational model where ultimately your application is just going to bring it up and turn it into a regular document anyways. But yeah, the indexing on that whole thing gets very interesting, and that's why it is interesting to hear that with Mongo you can index an array data type effectively and solve that kind of problem where people would typically do a comma-separated set of IDs or some other weird thing. I mean, I've seen some file system operations where they actually do a file system path, like you were saying, Jerry, but they do it with IDs from another table. So it's actually integers with slashes delineating them. But, okay.
Well, I've seen it done right and I've seen it done wrong. So trying to index on the full path and file name, it's wrong in my mind. If other approaches work better, I don't know.
Yeah.
And Morgan?
Yeah.
While we're still touching on some generic indexing stuff, so in the past MySQL geospatial and full text indexes were MyISAM based.
Yep.
And is it in 5.6 when they both became available in InnoDB, or is 5.7 where one of the
5.6 and 5.7. So full text was introduced in InnoDB 5.6, and geospatial is InnoDB 5.7.
Okay. And are you highly encouraging people that have MyISAM based for full text, for example, to come over to the Inno side?
Highly is relative. I'm highly encouraging.
But I mean, in practice, will an end user see a difference in size on disk or performance or you name it by stop using a MyISAM based full text and using InnoDB?
So we use a different ranking algorithm with InnoDB full text than MyISAM.
Mm-hmm.
We chose to use something similar to how Sphinx implements ranking for InnoDB. And so from that perspective, I think it's better, but from a migration path, maybe uses a locked into the quirks of the previous behavior.
Okay.
If it was a greenfield project, absolutely for sure, InnoDB is the better choice.
And you mentioned actually geospatial indexes, and it might be worth there talking about that they work a little bit different because you can query by difference. So the implementation of 5.7 is the same as the MyISAM implementation, or is it somewhat different? Because in MariaDB, and I hate to say this, they implemented geospatial indexes with InnoDB and a number of improvements, but you really don't have in InnoDB or XtraDB the distance querying, where you can query, give me the points that are a mile in a circle around this other coordinate, or
right,
that are within range of this polygon, or something like that.
So I'll try and guess that because I don't know how it works in MariaDB. Based on how geospatial indexes have to work, they're a slightly different structure than the B tree that Tim described, where there's really 2 dimensions. And so it's a R-tree index. So we implemented R-trees into InnoDB for 5.7 as the underlying structure. And it does make those 2-dimensional, where you're trying to find within a box, queries very fast. For the actual data type storage on disk, and for the queries, we use something called the C++ library Boost, their geometry features, and we've made some contributions to Boost geometry, and we've contributed them back as well upstream. If that sort of answers your question. So you could do some geospatial functions, and you could store geospatial data types with a B tree, but to get the full value of that 2-dimensional nature, you need to change the index type to use an R tree.
Yeah, that was the answer I was looking for.
So does that mean when you're defining an index that you want to use for geospatial type queries, you have to explicitly say R-tree in the index clause, or how does that grammar look for a database administrator?
I don't know. It's kind of embarrassing.
I'll pull it up real quick.
Jeff,
I'm really weak on
I think that's
geospatial.
part of it, but you definitely, when you're creating that index, also have to let MySQL know, what columns represent the shape data, right? Because shape data is an interesting beast as well. So I would assume it's like using type R-tree or some.
Yeah, the data type is called geometry. I know that much.
Yeah, but the definition is quite different than the regular data, and
The
when you
structure-
specify geometry, you have to specify what kind of geometry. So you can define a polygon, a line, or a circle, or an area, and then it works from there. And the R-tree, what it gives you is the possibilities to say, and it's not straightforward like a regular query as well, as far as I remember.
Yeah, I find the danger with geospatial is if you haven't played with it before and you think you're going to do it over lunch and just enjoy it, plan to lose the rest of the day, because you'll find like a map of the world or something, geospatial data points, you'll put it into your table, and then you'll be like, hey, let me run the query that shows me all countries that border Germany. And it's like, wow, that's really cool. Now, and before you know it, you'll look up and you missed 2 meetings and it's time to go home. So
Yeah,
it's a dangerous
I know
toy.
There's a blog on the MySQL server team blog. A post there where Matt Lord explores using the new geometry features in 5.7. I wonder if we can paste that in.
And in the MariaDB, and this is not to compete with you, Morgan, but in MariaDB blog role, there is a couple of blog, one by Kai Arno, an ex-MySQL alumni, that show how to query and to write special data that it should work as well with MySQL or MariaDB. And it's as Tim says, once you start playing with it, you can spend too much time onto it.
Yeah, give me one sec. I'm just pulling up all these different things. So what you were saying, Jerry, under the MariaDB knowledge base, there's a whole bunch of stuff about geographic features and then spatial indexes. And yeah, what you had mentioned, Morgan, the grammar is effectively it's something the geometry keyword needs to be in your data type, and then defining a spatial index. And then I believe this is the InnoDB server team post you were talking about.
I thought it was Matt that was the author, but maybe that was the one.
Oh, if you find it, send it my way. I will happily add that to the notes. But yeah, I just remember before I came and started working out here on the West Coast, GIS at the time was all about using Postgres. Like everything with GIS was always PostgreSQL, and then suddenly all of this work around MySQL spatial indexes got a lot more buzz at the conferences, and then with 5.7, having them move to InnoDB, so it's just an interesting thing to hear about, and it's one of those. Yeah, I've never used it. I would love to see how it looks though.
Yeah, I give credit. That what's coming in 5.7 in Inno. What's nice is they implemented the R trees and not just doing it around B trees, because we took a very high level overview of B trees here, but by going with R trees, you're getting, I think, additional functionality, but also performance. I think stuffing that data in B trees can certainly be functional, but not very performant at all. And to Jerry's point, maybe some of these implementations just refuse to do these kind of near queries because it would just be too slow if you had any amount of data in your system. It would be a full table scan and a whole lot of math.
Yeah.
That it's more efficient to say, let's not support the query because it's going to be very unsatisfying for the user anyway.
And real quick, I just wanted to show, this is what Morgan was talking about, the GIS example on the server, InnoDB server team. Talks about setting it up, importing some data, and just kind of going to town with it. So I'll be sure to throw this in the show notes. This is pretty good stuff.
Perfect. I'll send the team your thanks, Tim. I know it was very complicated to do the R tree. I heard right down to things like the locking manager had to change to do the 2 dimensions.
Yeah, when when I was at the show and I saw that and I talked to my guys, they all said they did what? Because we have no desire to implement another completely different data structure inside our stuff. That's a lot of work, and when you get performance as the result, I think that's what makes it important. And supporting all the real queries, because then to your point, Jeff, suddenly Postgres for GIS isn't the only option that's usable.
Yeah, sorry for the pause. Looks like Jerry just sent me something.
Yeah, I'm having problems with the MariaDB blog, and I don't want to start shaving that yak right now.
Okay. Just searching for the GIS tag on the MariaDB.
Yeah, that one there actually explains very well GIS in general, and jQuery is an open source project that allows you to query geographical data in a more natural way. That if you had to do it by hand writing SQL, you'd be, yeah, that's the one I was looking for. Those are the ones, yeah. And there's two bloggers there. One is Rasmus, and the other one is Kai Arno, as I was mentioning. The two of them, and they have full examples with code and everything, so you can reproduce the whole thing on your own.
Cool. Thanks for sharing. Alrighty, we are just about out of time. So I'm kind of picking up that folks want to talk about indexing a little more, maybe a little bit.
I feel excited to talk about the insert buffer. Actually, with Tim bringing that up.
If you could do, Morgan, if you could do some more digging, because I've always wondered why the thing doesn't just get as big as it wants. And obviously there's some tipping point where letting it get too big would crush performance. So, but playing with it off and on, you'll see it's like going back to the days of the 90s when you had a system and you had a little bit of extra memory you applied a disk cache to, and your system was suddenly usable again.
Yeah, it used to be 50% of the InnoDB buffer pool was the maximum size for the insert buffer, and it used to take up to 5% of InnoDB I/O capacity to do the background flushing. And I remember some other specifics about it, but the other one worth mentioning is it doesn't really trigger until your indexes start not fitting in memory. So if a page is already memory resident, it doesn't unnecessarily use the insert buffer.
Yeah. The other thing, if you do peak, and you tend to blog about these things anyway, any of that information about it that's instrumented in show engine status or global status, I would love to have a peek at that and see when I'm running benchmarks to understand what it is actually doing behind the scenes.
Okay. I think we might be able to get some performance schema data out of it. I have to. Okay.
All right. I've got to scoot. I've got my usual company meeting in 2 minutes. So nice talking to you guys. I'll see you all in 2 weeks.
Yeah. Thanks very much for the presentation, by the way, Tim.
Sure. No problem.
Alrighty. So yeah, it sounds like maybe some continued indexing, and maybe we can get some stuff from Mark about using performance schema to extract more data around that and the use of that, and just spatial indexes. I kind of want to sit and play with this stuff now. But yeah, are there any other things that folks would want to talk about with respect to indexing, or maybe just completely unrelated to indexing next time?
I tried to unmute, but I'm not sure I'm on, and my machine is frozen.
You are good, Jerry. We can hear you.
Okay. It was frozen for me. Anyway, indexing, well, geospatial indexes, we did, I believe, 2 podcasts on that, and I can try to find them. But it's a lot of information, and you really need to think differently. You have to have a different mindset on how to query the data, because it's not as linear as regular SQL would be.
Okay, cool. Yeah, feel free to send those my way. I will throw them in the notes. And anything else from you, Morgan, maybe for next time, or?
Yeah, well, I was just thinking about what you were saying, and if we could focus on other index types like the full text and the geospatial, we kind of spoke to them, but we gave our amateur rendition of that. I might be able to ask the author of that geospatial post if he's available to chat, Matt Lord. So I'll.
Yeah, that sounds pretty good.
I can bring him on.
And I think Ike from Flight, he had actually, the reason I thought of just talking about indexes was he had posted a blog post on full text indexes. I was hoping he would show up today to talk about it. But...
Yeah, he looked at the different ranking behavior. Ike's post was great. I loved it.
Okay, so I will see if I can get Ike to come on next time to talk about that and just kind of show it off, I guess.
Yeah, I was trying to think if we can get the people from Sphinx, but Alexander actually is based in Moscow, so this time of day he's sleeping.
Yeah, that's a hard time.
Yeah, he's farther east than Shlomi, or about the same time zone. Yeah.
Okay, well, it sounds kind of like at a high level indexing. We'll do a continued talk about it and see if we get more in depth on it.
Maybe ping Shiri about it. She might be more familiar with full text indexing.
Alrighty. Cool, that sounds good. So I think beyond that, that's our time for today. So thanks very much for tuning in.
And I'll bring up some indexing features on MariaDB that are not on MySQL.
All right, Jerry, to bring up MariaDB indexing features.
Dynamic columns.
Oh, I've got a name on every one of these topics, so I can chase people down for them.
Yeah, remind me, just in case I don't show up, I'll give you the material.
Okay, Jerry to present or give Jeff material.
So the next one it's 10, so that will be the 24th. I might be on a car coming back from Portland. And I don't think making a presentation while driving might be a good idea.
Well, we'll figure it out then. We'll definitely we'll make stuff work.
Yeah, I might. I have a choice on when to drive, so I might wait until after the DB Hangops, depending on how work is. But
okay. Alrighty, so that wraps us up for today. Thanks very much for showing up, guys, and everyone who participated, and we'll see you all in 2 weeks.
No problem. Thank you very much.
Bye-bye. Thank you.